Hi everybody, welcome back to our next topic in physics today. What we want to talk about today is an effect you've probably noticed before, and certainly as a kid you were probably pretty excited about it. I know I was. And you might not have thought too much about it. We want to kind of explain what the heck you were seeing, and it's called thin film interference. So it's this kind of rainbowy pattern you see sometimes when you spill oil on water, or if you look closely at soap bubbles. So you see the sort of pattern on things floating on one another. Or if you look at like certain kinds of like mirrored sunglasses, you might see this sort of effect. And the question is why? And so this is called thin film interference. So let's try and explain that. So before we do that, let's go back and talk about reflection, transmission, and absorption. So remember those things we talked about with waves, the three things that can happen. And what we want to talk about today is reflection and transmission. But remember what happens is when light does go from one substance to another, some light is reflected and some is transmitted. So for instance, when if we're looking at, let's say, a soap bubble, if this is the film of soap here, when light's coming in and bouncing off the soap bubble hits you in the eye, you're not just seeing one wave, you're seeing two, because one wave bounces off the surface of the soap bubble, and one wave is going to bounce off the other, like the outer surface of the soap bubble, because some of that light's going to go through the soap bubble and then bounce off again. And so depending on how these two waves interact, whether they're in phase, outer phase, that sort of thing, we're going to see some different sort of things. So it'll either be dark or bright depending on how wave one compares to wave two. And so that's kind of how we wanted to deal with it. So in order to explain what we see, we have to explain how does wave one compare to wave two. Hopefully you can see that if wave one is in phase with wave two, they would add together and you'd see something that's bright. And if wave one was out of phase with wave two, they would destructively interfere and you'd see something that would be dark. So with that in mind, let's try and figure out what are we going to see in phase or out of phase. And so the one thing we do have to remember before we get too far is that a wave that reflects will be phase shifted by half a wavelength, or we also can say it's inverted if that first medium is faster than the second medium. So for instance, if this is traveling from air to water or air to soap or something where the refractive index is lower here and higher here, a phase shift will occur. So let's just consider for the time being something easy, monochromatic. So hopefully, I don't think actually I've used this word yet, monochromatic. So the word kind of makes sense. Mono means one, chromatic or chromo has to do with color, so one color. So one color light with a wavelength lambda traveling in air that is incidence on this film of thickness T. And we're going to say it has a higher refractive index than air. So that means it's slower than, light is slower in this film than it is in air. All right, so now that we've got that in mind, so here comes this monochromatic light. When it hits here, one wave, we'll call it wave one, bounces straight off. And because that happens, oh, I just noticed a typo. I'm going to pause it and fix it right now. All right, fixed now. Great. So wave two comes in, or wave one comes in here, and it's going to be phase shifted during this reflection because it's going from something fast to slow. So wave one will be phase shifted during this reflection. Wave two will not be though, because it's being reflected off of the other surface there. And so when it comes in, wave one will be out of phase from the reflection, but wave two will be out of phase because it's traveled a different distance. And so actually what's going to happen is that those sorts of two effects will cancel each other out. So wave two will be travel lambda by 2 further than wave 1, but wave 1 will be lambda by 2 phase shifted from the reflection. So that'll actually then mean that they'll be back in phase. And so what we'll see here is actually a bright spot. So this will actually lead to a bright spot for this monochromatic light. So if this were red light coming in here and this film were lambda by 4, you would see a bright color red here. Now if you keep going down and say, let's pretend our film were a little bit thicker. So let's say that our film were at lambda by 2 now. So the same sort of thing happens. Wave 1 will be phase shifted. Wave 2 will not be during its reflection. But now wave 2 is traveling further. So wave 2 is now going to be shifted by a whole wavelength because it's going to be traveling one half of a wavelength here and one half of a wavelength here. So it's going to be traveling a whole wavelength difference, but wave one has been shifted. So now they'll actually be out of phase by lambda by 2. And so that means we're going to have a dark spot here. And so again, we would actually see, if we're looking at this film, we would actually see nothing at this point. This would be a dark spot. This would be black or dark. There'd be no light coming from this one color. And so if we continue this process along, we imagine thicker and thicker films, and I'm not going to do it, but if we imagine we just continue this process along, we'd actually come up with a pretty nice pattern. Um, and this pattern just repeats itself over and over again because we're dealing with periodic waves, so of course we expect the pattern to be periodic. That in order to have a bright spot, the thickness of this film has to be given by this expression. Um, I've given it the subscript REF for reflection. You'll see why in a minute here. But if I want it to be bright, it has to follow this pattern, and M is just any integer, or I guess non-negative integer, so 0, 1, 2, 3, 4, blah, 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 blah. And that'll tell me the thickness here. So for instance, if I put 0, I'll have it's a quarter lambda, or 3/4 lambda, or 5/4 lambda. So that would be all giving us a bright spot. And if you want to have a dark spot, you'd have to follow this expression. So I could have that the thin film could have almost no thickness, uh, lambda by 2, lambda, 3/2 lambda, so that sort of thing there. All right, so hopefully that makes sense. Okay, so again, notice something that we've kind of glossed over, though. We were trying to explain this cool rainbow pattern you see. But we kind of just talked about bright and dark spots. Well, the cool thing here is that we actually do have wavelength dependence. So that just because one wavelength will be dark, another one's going to be bright, or vice versa. So if I go back to this expression here for a second, one wavelength being bright, another one could be dark with the exact same thickness because they're not going to have the same lambda here. And so what that means is, which is cool, is that even though the film right here is some given thickness, that doesn't change. It's a bright spot for this violet color, but it's a dark spot for this orange color. And so all you see is, of course, the bright color. And so I think that's kind of cool that this is that rainbow pattern. And also notice also that these colors repeat. Like there's blue here and blue here. There's orange here and kind of orangey here because our expressions are cyclical. We have this sort of repetitive pattern because we can have the same thickness or different thickness films producing the same effects. So again, I think that's pretty cool. And something else that's kind of I glossed over here. Just if you look just at this equations, it looks like, okay, if I want to have light, I have to have this exact condition met. And if I want to have darkness, I have to have this exact condition met. So you'd expect to see like the diffraction gratings, we have dark, bright, and nothing in between. But clearly from this picture, that's not true. And the reason that is, again, because we can have partial sort of constructive interference and partial destructive interference that the two amplitudes can add and not be as big as they possibly can be. And the two amplitudes can subtract and not be always 0. And so we get these amplitudes that are actually bigger and smaller, but not always maximums or zeros. And so the colors are brighter and dimmer, but not completely on or off. I kind of hope that makes sense. All right. So let's quickly repeat this process we just did. But now actually what we want to talk about is transmission. Because if you remember, we talked about reflection before, but we did say that light was part of it was transmitted, and so we just kind of ignored that light that went through. But that probably wasn't a good idea. So we can actually look at light that was reflected or transmitted. So let's repeat this process with transmission now. But the one thing to keep in mind is that we're actually dealing with light being transmitted, or pardon me, reflected twice. And so every time you have a reflection, you're actually losing some of that intensity to the light. And so transmitted patterns generally aren't going to be as bright as reflected patterns just because, well, every time you reflect, you're losing some energy. And so now we have two reflections instead of just one. All right, so let's look at this case again. We have our thickness of lambda by 4. And so wave 1 comes straight through. There are no reflections for wave 1, and so it's not going to be phase shifted at all. But wave 2 will be phase shifted a total of, that doesn't make sense. I'm going to pause. Sorry, 1 second, guys. Here we go. That's better. Sorry about that. So in this case, wave 2 has not been phase shifted, and we know that because the wave is actually coming and bouncing off of these spots. You think it might be a phase shift, but remember, because it's traveling from something slow to fast, we don't have that phase shift. So wave 2 isn't shifted at all, but it did travel further. It traveled lambda by 4 here and lambda by 4 here, and so that means it's going to be actually lambda by 2 out of step, and so we're going to have a dark spot. We continue this process on for um, a film that's lambda by 2 long, and we go through the same sort of thing, and we're going to get the fact that we have a bright spot here. We have this as lambda now for its phase shift. So it's out of phase, um, but it's out of phase by a wavelength, which means it's actually in phase, so it's going to be a bright spot here. Okay, so again, we imagine continue this process on forever and ever and ever ad infinitum, and we actually end up with some pretty nice expressions again for the thicknesses of our films. Notice again, I've added some subscripts here, trans for transmission. And the one thing, if you're keen, you might have noticed that these are actually completely the opposite of the reflection expressions. And so this is sometimes troubling for people. Um, I'm sorry, that's just the way the universe works. But in order to get a bright spot with transmission, we have to have it m over 2 lambda, and in order to get a dark spot, it has to be 2n plus 1 over 4 lambda. All right, so I've got a quick quiz for you guys. Let's see how keen you are. So here are two pictures. It's actually, well, it's the same thin soap bubble hanging in gravity. So this might be like, I don't know, a piece of metal, and there's a soap bubble hanging in here by like before you blow a bubble or something. So it's hanging in gravity. And one of these is actually a transmission, and the other one is reflection. And I want you to think about which one is which. So which one of these shows transmission, which one of these shows reflection. And I've actually given you enough information to actually solve it right now. So think about it for a second. Um, if you think you can do it now, pause the video. If you think you might be a little stuck, I've got two hints I'll give you, so you can wait a second and I'll show them to you. But if you think you've got it or you want to get it before I give you the hints, pause the video and come back when you think you've got it. All right, so you've either got an idea or you want the hints. So I'll give you the first hint here. So the first hint, so if we're talking about gravity pulling it down, where would you expect the film to be the thinnest? So where in these, well actually where, this is one soap film, so where in the soap film would it be the thinnest if gravity's pulling it down? So again, there's my first hint. I do have one more, so again, pause it if you want to. All right, and you're back. So the second and last hint for you, what conditions would we have to have in order for a dark spot to occur for all wavelengths? So those are my hints. I'll let you think about it for a second. Again, pause it, come up with an answer, and come back when you've got one. Great, so hopefully you got an answer for me. And really, if I go back to my transmission and reflection ones, the key here again, as I said, the dark spot. And the dark spot is right here. This is dark for all wavelengths. And what sort of conditions could give me dark for all wavelengths? Well, if I take a look at, let's go back to actually both expressions here. So if I look at the dark spot for transmission, the dark spot for transmission, are there any conditions I can put in here to get a dark spot for all transmissions? Is there any sort of thickness I can put in here, n or lambda, or actually, sorry, not lambda, any n's or thicknesses I can put in and get 0? And the answer is no. But if I go back and I take a look at um, the dark spot for reflection, the answer is yes. If I have a film that is so incredibly thin, we can almost ignore its thickness, and that would be the n equals 0 case, then all wavelength, no matter what the wavelength is, the transmission thickness, or the reflection thickness can be 0. And so that's the kind of big clue here. This one over here, just let me get a, so this guy right here, this is your transmission. Or sorry, I said it, but I didn't write it. This is your reflection. We know that again just because of what conditions can give me a total dark spot. And this one over here, if you notice up at the top, that's really bright. Look at all those brightnesses there, and that's again because we have transmission. We don't have a dark spot for all colors there. All right, so that was a pretty Good question for you. All right. So let's kind of summarize what we just got. So here's our four expressions for how thick a film needs to be in order to get a darker or bright spot. So the M I'm using for maxima again, just like I did for diffraction gratings or Young's double slits or double slit, or sorry, yeah, I guess those two so far. And I'm going to be using N for minima or dark spots. So for reflection, it's these two. For transmission, it's these two. And let's see if we can apply this to a question here. So here's again, our four expressions. Let's look at our first example. So we're in the bright sunlight. We look down on a film of soap floating on top of water, and we see that it's a dull red color when we observe it from above. And I want to know, what is a possible thickness for this film? So let's start by kind of drawing what we're seeing here. So we've got this. Ooh, let's try that again. So we've got this here. So this is water down here. We have some film on top. We don't know how tall it is, or sorry, how thick it is. So I'll label it T. And when I have light come in, that's a red color. So I'll take red, and I view it from above. So that's this case here. We have a reflection here and a reflection here. I'm going to see a bright spot. So I know I have to have this as a bright spot here for reflection, and I want to know, what is the possible thickness for this film? So again, I'm going to have you try this one, pause it. When you come back, when you think you know a possible thickness for this film, I'll continue on. All right, so hopefully you're back with me, and you're going to jump on and help me solve this one. So if we're talking about reflection here, we know that because we're viewing it from above, and we're looking for a maxima or a bright spot. We're going to be dealing with the 2n plus 1, or 2m plus 1, pardon me, case. 2m plus 1 over 4 times the wavelength. We know the wavelength is 800 nanometers. Of course, you're going to use meters as your length. But what are we going to use for m? Well, it says a possible thickness, so we can use whatever m we want. So we could use 0, 1, 2, 3, 52, or 12. I'm going to pick 0 because, well, why not? And so if I do that, I'm getting a wavelength then of, or sorry, a thickness, 2.00 by 10 to the minus 7 meters. All right, so that's a pretty thin film. So we have this very thin film of soap floating on top of water, 2.00 by 10 to the minus 7 meters. And the second part of the question, what color would it appear from under the water? And that's kind of interesting if you think about it. Because I really want to know, okay, well, what's going to happen now? Because this ray is going to continue on, and this ray is going to continue on, and what's it going to look like underwater now? So now we're looking at underwater, so we're looking at transmission. We know the thickness of our film, and we're looking for a bright spot. So we're looking for T equals M over 2 lambda. All right, so we know our thickness, we want our lambda. The only question again is, which M should we use? And so we have a couple options. If we try the easy way and put M equals 0 in, well, that's not going to work so well, because in order to then solve for lambda, we have to divide by 0. And again, unless we know how M approaches 0, we can't do that. So let's go with our next easiest option. Let's go M equals 1. And if we do that again, rearrange, I'm getting lambda is equal to, 400 nanometers, which if you look it up, that is in the purpley range. Violet, I think, actually, whatever you want to call it. And so that's kind of neat. That so if you're looking at above from this soap film, it would look red, and if you're looking from below, it would look purple. And something else, a bit of an aside, but I think it's kind of neat to realize that it's not the color of the soap you're seeing, it's the color of the light you're seeing. And so really it doesn't matter what the film is, as long as it lets light in and doesn't change it itself, you can actually see all sorts of color from a thin film. All right, so I think that's it to me for today. I hope that makes sense, and I'll see everybody in class tomorrow. Have a good night, guys.